In this video, we're going to look at deriving the transfer function from the circuit. We'll look at some simple examples, and then we'll make some generalizations. So in the last video, we showed how an RL circuit acted as a low-pass filter, because at low frequencies, think 0 DC, it acts as a short circuit, so it lets everything through. At high frequencies, say infinity, it acts as an open circuit and lets nothing through. So in general, it lets the low frequencies in and blocks the high frequencies. So an RL circuit is a low-pass filter. So let's just look at don't know what happened there. Let's look at a generic RL circuit. And we have our voltage here, and this would be J omega L, and this would be R. And so our voltage out is going to be our voltage over the resistor. So V out, using voltage division, would be Vs times R over R plus J omega L. So V out over Vn, which is our definition of our transfer function, H of omega, would be Vs times R over R plus J omega L, which is V out, over Vn, which is Vs. So then this is Vs over Vs plus R over R plus J omega L, which is 1 plus R over R plus J omega L. Actually, I don't, no, forget that. Okay, I'll just edit this out. All right. So the VS's cancel, and I get H of omega equals R over R plus J omega L. So now if I rationalize this, so I would multiply by R minus, actually, rather than rationalize it, let's get the magnitude. Well, no, let's go ahead and rationalize it, and then we'll get the magnitude. So I'll multiply by R minus J omega L over R minus J omega L, and I get H of omega equals R squared minus R J omega L over R squared plus, the J goes away, that was the point. So it would be minus J squared. J squared is -1, so minus -1 is 1. So plus omega squared L squared. So now if I want to get the magnitude of this, so the magnitude of a complex number, so the magnitude of a complex number is the square root of the number times its conjugate. So the magnitude of H of omega would equal R squared minus R J omega L over R squared plus omega squared L squared times R squared plus R J omega L over R squared plus omega squared L squared. and then take the square root of all that. So that equals the square root of r squared minus plus, because it'd be minus j squared plus r squared omega squared L squared over r squared plus omega squared L squared squared. Then I can factor an r squared out of the numerator, and then in the denominator I get r squared plus omega squared L squared squared times r squared plus omega squared L squared over 1. So if you look, I just factored an r squared out of the numerator, and I was left with r squared plus omega squared L squared. Now this first part, I can take the square root of that, so that's r over r squared plus omega squared L squared times the square root of r squared plus omega squared L squared. And now you'll notice those two things are the same, so that's the same as r over, because this would be to the first, and that would be to the 1/2, so r squared plus omega squared L squared to the 1/2 over r squared plus omega squared L squared to the first. So if I subtract exponents, I get a 1/2 in the denominator. So r over the square root of r squared plus omega squared L squared. And let's see, is that correct? That is correct. So they write it in a different way. So they factor an L squared out of the denominator. So if I factor an L squared out, so factor this L squared, and then I'm left with r squared over L squared plus omega squared. And then I can take that out. So r over L times the square root of omega squared plus r over L squared. It's not supposed to be squared. Or the r is supposed to be squared. Yeah, this was squared. And then this r over L right here, I can put those together in the numerator as r over L over the square root of omega squared plus r squared over L squared. So now we can see, we look at our original transfer function, right here, r over r plus j omega L. If you look at r over r plus j omega L, where is that going to be maximum? Well, we already know that we would have maximum, well, you may not know this, but we'd have maximum where the imaginary part would equal to 0. But that would also be the case, because when you have a fraction, it's biggest when the denominator is smallest. And so if we make j omega L as small as possible, with omega equal to 0, then this becomes r over r. Yeah, so it's maximal when the denominator is smallest, right? And so that would be 1. But that's also going to be true for these passive filters. Your max gain is going to be 1 for most of your passive filters. So H max equals 1. So for what frequency is our magnitude of our transfer function equal to the maximum divided by the square root of 2? So the corner frequency, so omega c happens whenever h of omega c equals h max over the square root of 2. So if I plug omega c into this, I have r over L equals the square root of omega c squared plus r squared over L squared equals h max, which is 1, so 1 over the square root of 2. Square both sides, r squared over L squared over omega c squared plus r squared over L squared equals 1/2. R squared over L squared times 2 equals omega c squared plus r squared over L squared. Subtract r squared over L squared from both sides. 2r squared over L squared minus r squared over L squared is just r squared over L squared equals omega c squared, or omega c equals r over L. So for a RL circuit, our cutoff frequency is r over L, which would not be surprising. What do you think it would be for an RC circuit? Would you guess RC? Well, we'll see in a minute. Okay, so that would be our cutoff frequency. Now, let's say you needed to design a low-pass filter that would filter out frequencies over 10 hertz. So low-pass filter frequencies greater than 10 hertz. That hertz tells us that that's an F, not an omega. So F equals 10 and omega equals 2 pi times 10, or 20 pi. And so that's what we want our cutoff frequency to be. So our cutoff frequency, we would have 20 pi equals r over L. So now you would want to pick a value for your inductor. Let's say that we had an inductor that was 100 millihenries. What would our resistance need to be? So you just have 20 pi equals r over 100 times 10 to the negative 3, or r equals 2,000 times 10 to the negative 3, or r equals 2 ohms. Oh no, I forgot my pi. So that number's not right. So it's whatever that is. It is 6.2. Oh, well, it's 2 times pi. 6.28 ohms. And that would be your low pass filter.